Good afternoon. My name is Damiana Brabham, and we're in class CH131C, and we're in group 15.
Hi, I'm Jasmine Tramel.
Hi, I'm Alma.
Hi, I'm Alicia Mosley. Hi, I'm Deja Howard.
So today I'll be discussing part A, questions 1 and 2, where I'll be talking about Dr. Mary Daly, Florence Nightingale, and also matter. Dr. Mary Daly was the first African American woman to earn a PhD in chemistry in the United States. Her groundbreaking research focused on chemistry of nucleic acids, proteins, and the effects of high blood pressure on the human body. She made important contributions to understand the link between hypertension and heart disease, paving the way for the future medical advances. Florence Nightingale, often called the founder of modern nursing, transformed healthcare through her focus on hygiene and sanitation. During the Crimean War, she improved the conditions, which drastically reduced death rates. Her dedication helped establish nursing as a respected profession and created lasting reforms in public health. Now, question 2, matter. Matter is a substance that makes up everything in the universe, and it is built in a hierarchy. At the base level, matter is made of elements which are pure substances like oxygen, hydrogen, and carbon. Each element is composed of atoms, the smallest unit that still retains the properties of that element. Atoms themselves are made up of even smaller parts called subatomic particles: protons, neutrons, electrons. In short, matter is made of elements, elements are made of atoms, and atoms are made of subatomic particles.
Hi, so for part A, I'll be discussing questions 3 and 4. For question 3, chemistry and nursing. Chemistry helps pediatric nurses understand the why behind treatments, make safe medication calculations, interpret labs, and educate families about health. For number 4, isotopes are atoms of the same element that have the same number of protons and electrons, but a different number of neutrons. For the statement, the same number of protons and electrons, but different number of neutrons. For isotope notation shows both the mass number and the atomic number. For the mass number is protons plus the neutrons, the atomic number is the protons, and then you have the element symbol. For the 3 elements that I chose was carbon, oxygen, and nitrogen. For carbon has 6 protons, 6 electrons, and 8 neutrons. Oxygen has 8 protons, 8 electrons, and 10 neutrons. And nitrogen has 7 protons, 7 electrons, and 8 neutrons.
Good afternoon. I had part A, number 5, which was labeled a periodic table, and it's metals, nonmetals, metalloids, transition metals, intertransition metals, groups, periods, and noble gases. This is my diagram. It might be a little bit hard to see, but it's definitely there. So first, I'm gonna start off with my nonmetals. So everything in the green would be our nonmetals. See, green, green. And then everything in the yellow are your metals. And then I'm gonna go into a little bit more detail on that later. And then for pink, we have metalloids. So yeah, and then, let me see. So these would be our periods, and there's 7 periods in the periodic table, and there's 18 groups. The groups go by column. So 1, 2, 3, all the way to 18, if you could see good. And then, so yeah, 7 periods, 18 groups, and these here would be our transition metals, just this section right here. Not anything up here, not anything up here, just down here, are the transition metals. And then down here on your periodic table, you might notice like a sub part, and those are our inner transition metals. And then another thing we have is our noble gases. Your noble gases are the last column, which will be group 18 in your periodic table. And yep. And for my element, I chose helium. The symbol for helium would be He, and then the atomic number is 2, and then the atomic mass is 4, and then the symbol is He. So yep, that's everything for my periodic table. If you have any questions, please let me know. Thanks.
For elements in nursing, I'm going to identify 5 elements, one from each type of metal, and then explain to you how it is used in nursing. For alkali metals in this area, I'm going to identify sodium, which is Na. Sodium is essential for nursing for maintaining fluid and electrolyte balance. Nurses often monitor sodium levels in patients to prevent hyponatremia, which is low sodium, or hypernatremia, which is high sodium. Sodium is also used for IV fluids like saline and used for hydration and medical dilution. Under alkaline earth metals, I'm going to identify calcium. Calcium plays a big role in bone health, muscle contraction, and blood clotting. Nurses may administer calcium gluconate or calcium chloride in emergencies such as hypocalcemia or cardiac arrhythmias. For this area in the periodic table, I'm going to identify iron, which is Fe right there. Iron is very essential for the hemoglobin production, and nurses often monitor iron levels in patients with anemia. For nonmetals, I'm going to identify oxygen. Oxygen is the life support for all humans. We need oxygen to breathe and stay alive. Nurses will need to monitor patients with respiratory issues like COPD, asthma, or pneumonia for oxygen. Lastly, I'm going to identify metalloids, which is down here. I'm going to identify iodine. Iodine is used as an antiseptic to clean surgical sites and prevent infections.
The first calculation is scientific notation. Scientific notation is a way of writing very large or very small numbers using powers of 10. My first example is 45,000, and you would go from the 0 here and move 4 decimal places to the left, and your answer would be 4.5 times 10 to the 4th. My second example is 0.0063, and from the decimal, you would go 3 places to the right. Your answer would be 6.3 times 10 to the negative 3. My last example being 1,230,000. The decimal will be at the end of the 0, and you will move it 6 places until you get to the 1, and your answer is 1.23 times 10 to the 6. The second calculation is density, and density is the amount of mass in a given volume of a substance. The formula is density equals mass over volume. My first example is a block with a mass of 200 grams and a volume of 50 cubic centimeters. So you would do 200 grams over 50 cubic centimeters, and you would get 4 grams over cubic centimeters. The second example being the mass is 1.2 kilograms and the volume is 0.4 liters. So you would do 1.2 kilograms divided by 0.4 liters, and you would get 3 kilograms over liters. Last example is mass 25 grams and the volume is 10 milliliters. And you would do 25 grams divided by 10 milliliters, and you would get 2.5 grams over milliliters.
For converting temperature, I'm going to show you 3 problems on how to convert Fahrenheit to Celsius, Celsius to Kelvin, and Kelvin to Fahrenheit. For problem 1, a patient's fever is measured at 102.2 degrees Fahrenheit. What is its temperature in Celsius? The formula for Fahrenheit to Celsius is Celsius equals parentheses Fahrenheit minus 32 times 5/9. For step 1, you're going to add 102.2 degrees Fahrenheit to this and then subtract 32 from it, and you're going to get 70.2. Now you're going to multiply 70.2 times 5/9, and that equals 39.0 Celsius. Problem 2, I'm going to convert Celsius to Kelvin. The storage temperature for a vaccine is 2 degrees Celsius. What is the temperature in Kelvin? Our formula is Kelvin equals Celsius plus 273.15. First, you're going to add your 2 degrees Celsius to 273.15, and that will give you 275.15 Kelvin. So your answer will be 2 degrees Celsius equals 275.15 Kelvin. For problem 3, I'm going to convert Kelvin to Fahrenheit. And in this, you have 2 steps because you can't convert Kelvin to Fahrenheit. It has to be Kelvin Celsius to Fahrenheit. An experimental lab is kept at 310 Kelvin. What is this in Fahrenheit? For step 1, you're going to convert Kelvin to Celsius, and the formula for that is Celsius equals Kelvin minus 273.15. So it's flipped. Then you're going to add 310 degrees Kelvin from the problem to the formula and subtract 273.15, and you're going to get 36.85 degrees Celsius. For the second part, you're going to convert Celsius to Fahrenheit, and the formula for that is Fahrenheit equals Celsius times 9/5 plus 32. So you're going to add this number into this formula for Celsius and multiply that by 1.8, which is also 9/5, which will equal 66.33. Then add 66.33 to 32 from the formula, and that will equal 98.33 Fahrenheit, and that'll be your answer.
Okay, so I'm going to be explaining metric prefix conversions. So metric prefixes are used to make very large numbers or small numbers into something easier to work with. So each prefix represents a power of 10. So we have some right here that I wrote down. So we have kilo equals 10 to the third power, which equals 1,000. Centi equals 10 to the negative second power, which equals 0.01. Then we have milli, which equals 10 to the negative third power, which equals 2.5 kilometers to meters. So what we're gonna do here is you have to realize that 1 kilometer equals 100 meters. So now we're going to multiply. So 2.5 kilometers times 100 meters over 1 kilometer equals 2,500 meters. So now for the second example, we're gonna convert 450 milligrams to grams. So we have to keep in mind that 1 gram equals 100 milligrams. So we're going to multiply again. So 450 milligrams times 1 gram over 100 milligrams. That will equal 0.450 grams. Now for the third example, we are gonna convert 0.032 from meters to micrometers. So we have to realize that 1 meter equals 1 million micrometers. So now we're going to multiply again. So it'll be 0.0032 meter. Okay, so now we're going to get into example 3. We're going to convert 0.032 meters to micrometers. So 1 meter equals 1 million micrometers. So now that we know that, we're going to multiply. So 0.0032 meters times 1 million micrometers over 1 meter equals 3,200 micrometers.
For part B, I'll be doing question number 5, which is conversion between base units. So for the 3 examples, the first example is to convert 2,500 milligrams to grams. So we know that 1 gram equals 1,000 milligrams. So we're going to write it as 2,500 milligrams times 1 gram over 1,000 milligrams. And then we're going to cancel out the milligrams from the 2,500 and 1,000 to leave you with grams by itself. And then your setup will be 2,500 over 1,000 grams. And then you'll simplify that. After you divide, it becomes 2.5 grams. So your answer is 2.5 grams. For the second example, we have 3.6 kilometers to meters. So we know that 1 kilometer equals 1,000 meters. So your setup would be 3.6 kilometers times 1,000 meters over 1 kilometer. You then cross out both the kilometers on both sides, which will leave you with 3.6 times 1,000 meters. And once you multiply those, you end up with 3,600 meters. And for the third example, I have 0.075 liters to milliliters. And 1 liter equals 1,000 milliliters. So 0.075 times 1,000 milliliters over 1 liter. You then cross out the liters on both sides, which will leave you to 0.075 times 1,000 milliliters. And once you simplify that, that becomes 75 milliliters.
Good afternoon, it's Damiana Brabham, and for part B, I chose significant figures. Number 1 is, first I'm going to explain the rules of sig figs. So, number 1, all numbers that are not 0 are significant. Number 2, zeros in the middle of non-zero numbers are significant. Number 3, zeros after the decimals are significant. Number 4, zeros and coefficients in scientific notation are significant. Number 5, any leading or beginning zeros are not significant. Number 6, zeros in a large number without a decimal are not significant. Sig figs are the digits in a number that contribute to its precision, including all non-zero digits, any zero between significant digits, and continuous zeros and decimal portions. So for my first example, I chose the number 2.1390. And the way that I broke it down was the numbers 2, 1, 3, and 9 are all non-zero and significant. And the trailing zero after the decimal point is also significant because it indicates precision. So when you put it together, 2.1390 gives you 5 sig figs, 5 digits. And that's my example 1. Now for my second example, we have 0.40001. 4 and 1 are non-zero, which means they're significant, and zeros between them are significant as well. So 0.40001 has 5 sig figs. And for my final example, 91630, 9, 1, 6, and 3 are non-zero, and there's no zero between non-zero digits, those non-zero digits. So 91630 would give you 4 sig figs. And if you put the decimal after the zero, it would be 5 sig figs, if that makes sense. Thank you, and have a good day.